from 2 to 4. And then there's an idea I didn't get to last time. So I'm going to do the idea first and then pick at a couple homework problems. The intermediate value theorem is the idea I didn't get to yet. Intermediate switch of shit. Hello, Internet. I forgot to change my board.
Are you muted?
No, that's all live.
Are you recording?
Yeah, I'm recording. Okay, there we go. Now people can see the back of writing. Intermediate value theorem. And I'm just going to give a slightly less technical version of the intermediate value theorem. So you've got some continuous function. So f of x is continuous. From x equals a to x equals b. All right, so quick snapshot. Here's x equals a, here's x equals b, and the function does something in between there and there. Maybe it's straight, maybe it's wavy, but it's a function in between a and b. And it's continuous. And we talked about the definition of continuity yesterday. It means limits are nice at every point. That's the way to think about it. So this is going to lead to some y value. We'll call that f of b. And there's going to be some y value over there. We'll call that f of a. And in this case, I have f of b above f of a, but it depends on the function. Okay, so it could be any which way there. So if we pick some value, let's say z, and that z is in between f of a and f of b. So it's a y value. So that, let's see. Pick z between f of a and f of b. And I'm writing English here because I can't use it in inequality because I don't know which is bigger, f of a or f of b, because this is a general situation. What the intermediate value theorem says is there has to be some x value in between. So there is an x in that interval AB where f of that x value happens to be that y value we picked. So bottom line is, if we have a continuous function between 2 points, for any y value you pick, there's an x value that goes with it in the interval you started with. Seems like, yeah, right? Doesn't seem like kind of obvious. But it turns out it's an important, powerful thing. And you've actually used it before in other math classes. Yeah. So what's that? Yeah. You have, yes, you actually have. You played around in a previous math class with zeros of polynomials. And if I have some polynomial, it's called p of x. If in some interval, let's say p of a is positive and p of b is negative, what y value has to be in between positive and negative?
0.
Yeah. So z, there's got to be a z equals 0, right? Z is a y value, according to the intermediate value theorem. So there's got to be a place, p, an x value where I'm going to get a 0. Otherwise, if that doesn't happen, the function is not continuous. We've broken it somewhere. Okay? So this is one application of the intermediate value theorem. If you have a function that goes from positive to negative, it's got to have a 0 in between. And then you can go and search for that 0. And in college algebra pre-calc, you guys learn techniques for trying to find that number in between. Okay? And there's a whole bunch of different techniques. The most common is factoring, but there's other ways to find it. So that's the intermediate value theorem. This blatantly obvious idea that is very important for everything we do. All right, so couple of homework problems. One is based on that, one is not. So let's see, that was 2-3. Let's go to 2-4. UT. All right, so this is an intermediate value theorem question. Blow it up huge. So suppose that f is a continuous function, f of -2 is -8, f of +2 is 8, determine which choice best describes the statement. So this is based on knowing the intermediate value theorem. So on the interval from -2 to 2, this function goes from negative to positive, true? What has to happen?
Has to be 0.
It's got to cross the axis, right? It's got to cross that x-axis. So f of x equals 0 for some x in an interval. This is sometimes true, sometimes false, always true or always false.
Always true.
Yeah, if it's continuous, it's got to be true. Otherwise, it's not continuous, right? So always true. Done. Not bad. All right, everybody better get that one right. Okay, let's back up. So that was the intermediate value theorem. Boom, done. Oh, this one is fun. So here we're given a piecewise function, but one piece is like not quite fully defined. They're saying, hey, part of it's a straight line. It's got this y-intercept, but I'm not going to tell you the slope. But what we want to have happen is we want this to be continuous. Are piecewise functions always continuous? No, sometimes they're broken, right? So for some values of m, these guys are not going to connect. For one value of m, they are going to connect. So let's see if we can figure that out. Okay. Copy that into my little clipboard. New page. Snip. I just want that part right there. So did you all figure out how to enter piecewise functions into your favorite graphing thing? Mm-hmm. Okay. If you haven't, it's something you really want to try and play with. Is it essential for the test? No, not really. You can do it by hand. So I'm just gonna play with this by hand for a second. I'm just gonna graph the part I know right now, and I'll do the other part in a sec, and then we'll play around with a little algebra. So let's see, what do I know about that right there? Well, it's gonna have a vertex, x equals -b over 2a. Do you guys remember the whole vertex thing of a parabola? Sort of, kind of, not really. All right, so that would be -9 over 2 times 1. So at -4.5, there's where the x value of the vertex, that's the axis of symmetry, that's where that is. If I plug that in here, I get the y value. So somebody whip out a calculator for me. -4.5 squared plus 9 times 4.5 minus 3.
9 times -4.5.
-4.5, yep, there we go, thank you, Sam. -63.75. Oof, that's way down there. -63.75. Anybody else get that? Yep. Okay, so let's see, -7 is our cross. So let's see, I'm just gonna rough sketch this sucker. Let's see, let's say that's negative, whoa, what happened to my pen? -5, let's say that's -10, +5, +10. This way I'm gonna go 10, 20, 30, 40, 50, 60, 70 is way down there. So the vertex of this sucker, let's do it in blue, is 63, -7. So it's somewhere in that vicinity. This parabola opens up or down? Up, because it's a positive x squared right there. Okay. So it opens up and it has a y-intercept where? No, this would be the vertex. So the vertex is -4. Put that number in the wrong spot. Move that sucker over. Yeah, the y-intercept is -3. Sorry, let's see. The -4.5 is around here. That's the axis of symmetry. The vertex sits more like right there. And -3 is about right here because I'm scaling by 10. I guess I should write that in. -10, 20, 30, 40, 50. There's -60 right there. So this parabola is going to have a matching point over here somewhere to that -3. That's going to end up being at -9. So here's that parabola right there to the best of my artistic ability. Imagine it's not so pointy at the bottom, but at this scale it's hard to tell. All right, so then we want to cut this off. This is only for x greater than or equal to -7. So -7 is about over here-ish. Say, so that's where I'm going to chop it off right there. I wanted, oh well. And do I get an open circle or a closed circle there?
Close.
Closed circle because of the or equal to up there. All right. Now, I also have a straight line there, and I'm going to use my line tool. Where's my line tool? Here, there, there. Let's make that red. With a y-intercept of -10, and the slope could be positive or negative. So let's just say that's my line right there. But we don't know the slope of it, right? Just a little bit. There, there. So this line could be slope positive, it could be slope negative, right? And I'm only concerned about the part of it to the left of that vertical line at x equals -7. That line right there. So can you see that there's going to be a special slope for which those guys are going to match up to make it continuous? So we got to find that special slope. Okay. So guess what we need to know to do that? We need that y value. How are you going to find that y value? Just plug in x equals -7. Okay. So we want to know, according to this guy up here, what is f of -7? All right. Look at your calculators. Calculate that sucker.
-17.
Great. -17. Confirmation. Anyone else get that? All right, so if that's -17, we just need the other one to match there. So for us, we need our mx minus 10. It needs to equal -17 when x is -7.
You wrote -7 equals -7.
Oops, I missed the one there. There we go. So you see what you need to do next?
Yes, and check.
No,
Solve
you
for
don't need to guess and check it all. You just plug in -7 and solve for m. Yeah, write that down, give it a shot. What'd you get?
1.
M equals 1. Slope of 1 should do that. All right.
Same.
So let's see, slope of 1 should do that. So yeah, my scale is kind of hard to see a slope of 1 there. So I'm going to redraw this in Desmos. So if you didn't already, run through that algebra, check it out. 1 looks correct to me too. So in Desmos, graph f of x equals curly bracket. So let's see, we now believe that when x is less than -7, colon, it should just be x minus 10 for that line equation. And then comma, the other side is when x is greater than or equal to -7, colon, that's the parabola, x squared plus 9x minus 3. And if I scroll down to their intersection, oh, look at that, we nailed it. Look at, they meet there. If I put a different slope in there, though, they're not going to meet. Like if I throw a 2 in there, it's broken. If I throw a 0.9 in there, it's broken. The only time it's going to work out nice with a y-intercept of, what did I do there? If I fix it, there we go. Slope of 1 is the only time it's going to work. Okay? Slope of +1. Here the slope is 1. Right, so double check that math. We've got m times -7, that's the critical x value, minus 10 is equal to -17. So then -7m, I'm going to add that 10 to the other side, equals -7, divide by -7, and n is 1. Dylan, you okay there? So we pieced it together. We rebuilt that. All right, were there any other homework questions besides those last two?
Would 10 be the same thing
Let's see, which one was that? That was 11. 10. Yeah, 10 is the same idea. We just have to find b in that case. Yeah. So to do that, you plug in 7 into the top one, get the right y, and then set it equal to that down here. Yeah, and that'll work out. Yeah, we'll do that one for fun right now, too. New page, screenshots. Screenshot, there you go. So here we, instead of finding the right slope, we want to find the right y-intercept to let those meet. And so the trick there is making them meet at that x value. They have to have, given that x value, they both have to have the same y value. So first thing we need to do is say, okay, well, if we plug into the other part, that 7, oops, that gives us what, 14 minus 3 or 11? All right. So if y equals 11, what's the y-intercept for the other one need to be? So now, if I plug in 7 to the other part, I can calculate b if I know I want y to equal 11. So negative 49, add that to the other side. So if b is equal to 60, did I do that right? Mm-hmm. It should work. Okay. So how could I test that? I could test it in 2 different ways. I could rewrite this with the 60 there, plug 7 into both parts, make sure they agree on y, or I could graph it in my graphing thingy and see that they meet up. 2 different approaches to double check that. How many people have had to regenerate homework problems when you're doing them to try it again? Right? It happens to all of us, right? I'd like you to, wherever possible, before you hit submit, think, how could I double check this? Because remember, on the test, there's no submit and check on a written test, so you got to be sure about it somehow. So think about that when you're doing your homework. How could I check this if this was on a test? How could I confirm to myself I just did that right? All right, moving on. So continuity was the main topic there. Intermediate value theorem was an important side topic. We're going to take a look at section 2.5 now, which is the precise definition of a limit. So we have some limit, and it's a pretty straightforward one. X approaches a of f of x. That limit exists. We get some number. We call it n. Now remember, that means comes in from the left to the same spot, comes in from the right to the same spot. Does f of a necessarily exist given that information? No. No. I don't know if f of a exists. That's a whole nother matter. I don't care about that. Okay. So f of a might not exist, but the limit does. Could be a tiny hole. So to precisely define what that means is it's kind of like a dare. So remember when we first started limits, we just plugged in x values that were getting closer and closer and closer, like 100th away, 1,000th away, 10,000th away, 100,000th away, and we looked to see if there was a pattern to those y values, right? And sometimes we were able to name that number. Like some people would say, oh yeah, that's a quarter, or oh, it's going to 2, or oh, look, it's going to e. Were there other cases where we could see that there was a pattern, but we couldn't give the number a name? That happens sometimes too, right? So the precise definition of a limit is basically kind of like a dare. And the dare is, how close can you get to the limit? Can you show me how to get that close? Which is the game we played at the beginning of chapter 2. So now I'm just going to formalize that. It's going to look a little weird and crazy. If you find this extremely exciting, then you're destined to be a math major. If you don't, then you're a normal person that's probably not going to end up getting a degree in math. It's okay too. So here's the way it goes. For all numbers called epsilon. That's a little Greek epsilon. Some subtitles in here. By the way, epsilon is destined to be a small number, but greater than 0. There exists, that's Greek delta. And guess what's going to be true about delta? No, not in this case. In this case, it's going to be a small number. A small number. If we were dealing with limits that go to infinity that weren't a real number L, then we would hit a large number. But here it's going to be a small one. And delta is also going to be greater than 0, such that if the distance between f of x and the limit, right? So when we look on each side, up and down, if that thing is less than that little number epsilon, then the difference between x and a has to be very small also, close to delta. So when I subtract two numbers, I find how far apart they are, true? Right? It's like 110 miles to the Dalles, it's like 200 miles to Portland. If I subtract those two, I get it's like 90 miles from the Dalles to Portland. So when you subtract two numbers, you get how far apart they are. But if you subtract in the wrong order, you get a negative number sometimes, true?
Yes.
So throwing absolute value around there just says, just look at the positive version of it, in case we subtract in the wrong order. Okay. So just some other subtitles here. When I write something like this, a subtraction with absolute value, that just means distance between. So the distance between any function value and the actual limit, if that's small, if we're close, then what I should find is that the x value that I'm playing with at the time has got to be close to that value a that I'm trying to get to. Distance between also. That's close to. Okay. So I'm just going to show you a little a hand-drawn graphical thing, and then I'll show you a cute computer-drawn graphical version of this, and then we'll play with this idea in a couple of examples. And so the way remember I said it was a dare a minute ago. So let's say Henry just did a limit, and he said the limit is e. Right? He's playing with some function. He says limit's e, Gary. I'm sure of it. I said, okay. I would say, can you tell me what x value I should pick to get within 1,000th of that limit? And he says, yeah, blah, 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 blah. He says, pick x equals this, and that'll get you that close to it. I said, okay, can you get me within 1,000,000th of e? And he'll do a calculation. Say, yeah, pick this x value. That'll get you within 1,000,000. So it's just a matter of saying, how close do you want to get to the actual answer? Which x values get you that close? That's what this definition says, which is what our experimentation was in the beginning of chapter 2. Those tables we made where we pick x values that were getting closer and closer to a, and we prayed, we saw a pattern to whatever that limit was L. So, picture of all of that. I've got some function, f of x. I've got some value x equals a down here. And I trace up. Now, it may or may not exist at that point right there, so I'm going to throw an open circle there for now. It doesn't matter whether it exists or not. At a, what matters is that whether I look to the left or the right, it's getting close to this value L. Okay, so L is my limit here, the y value. Now, epsilon is how far away I am at any point. So, let's see, it's black again. So if I pick some x value, say right there, and let's suppose we're really zoomed in, so I'm pretty close to A, right there. That x value is going to trace up here, and there's going to be a corresponding y value over there. That little distance right here, in between those two, that little distance away from L, that's what we call epsilon. So in this case, I can have that on either side. So I could be a little above or a little below. So here or there. So I've got this upper y value, that's L plus epsilon. I've got this lower y value, that's L minus epsilon. So I'm on each side there. So Henry's sure he knows what the limit is. I say, okay, can you get me like this close to that limit? And he would just say, yeah, I can just trace back here and say, if you pick x values less than whatever that is right there, but on, to the right of A, or you could go to the other side and say, if you pick an x value that's bigger than whatever that number is, if you pick any x values in between there, you're going to get close enough to L, is what he's telling me. So it's the definite process definition just basically shows us how to zoom in on that one, which we already know how to do. We're just putting it in other terms. Down here, this number over there, that's kind of like the x plus delta, that little bit to the right, or this over here could be my x minus delta, a little bit to the left. So that's it kind of broken down. So a note on the absolute value inequalities I drew a minute ago. So hopefully you remember this from a previous math class, but if you don't, I'm going to show you now. So the physical interpretation of that is what did I say the whole left side of this is supposed to mean? Different distance between two things. What two things? Well, the distance between x and a. So what this says, one way to view it is the distance between x and a is less than whatever that number delta happens to be. Delta is a squiggly looking D. Another way to state that in English would be to say x is no more than delta away from whatever a is. So I can only pick x values that are no more than delta away, right? Because this says the distance has to be smaller than delta. So we can't go farther than that. It's setting up a perimeter for us. Next, does anybody remember algebraically how to deal with absolute value inequalities? One greater than, and then you got to throw a negative in there. Yeah, so there's a couple ways to look at it. One way to look at that, x minus a is less than delta, is to rewrite it without the absolute value. Would be to see x minus a has to be less than delta, but it also has to be bigger than negative delta. That's one way to rewrite it. I can solve this for x, right? How would I solve this for x? How do I get the x alone? Not subtract, but add. Yeah, so if we add a to each portion here, so plus a, plus a, plus a, then what happens? We're going to get x is in the middle. X has to be less than a plus delta. On the other side, x has to be greater than a minus delta. With me? Okay, what does that mean? Well, I got some x value. On one side of x is a boundary, a fence. That number is a plus delta. Oops, sorry, x is not in the middle. A is in the middle. Oh, shit, that's not eraser. Okay, there we go. On the other side, I have a minus delta, and x can be any number in the middle there. right? It's got to be above, a minus delta below, a plus delta. Does that picture match the idea of this inequality at the top? That x has to be no more than delta from a, right? So that was my verbal interpretation. If I do the algebra, I get a number line interpretation of that same number. Right? So all I'm saying is x has got to be between these two numbers, right? So the way, again, the dare works is you say you know the limit. I say, okay, fine. If you know the limit, then I need you to get to me within 1,000, say, of that limit. In which case, I'm saying epsilon is tens, hundreds, is 1,000. Then what you do is algebraically or graphically, you trace back and you figure out how far that distance over the x has to be so that I'm close enough. Say, okay, if you pick an x within 1/10, or maybe it's 1,000,000th of a, then you'll get close enough to it within your margin of error, 1,000. Right, let's do it. So, function f of x equals 3x plus 1. A, let's try 2. What is the limit as x goes to a of this function f of x? Seven. So that's what we're claiming L is, the limit, 7. Now in this case, the limit is the function value. That's continuity, but that's not relevant. Here comes the dare. I want epsilon to be 100. So what I'm saying is, can you tell me what x values I can pick so that I'm within 100th of that value set? Okay, so experimentally, how do I get there? So this is what I call the dare. All right, so how do we evaluate the dare algebraically to get me an answer? So looking back at the definition, right here, I've given you the dare. We put that dare into that expression and hope that we can morph it into that expression. Because if we can morph it from this form to that form, then we know how close to get over there. Okay. So I'm just going to write our goal on this page here. The goal then is to take the expression f of x minus L is less than epsilon and turn it into x minus a is less than delta. So I'll show you a couple ways to do that. Okay, what's f of x here? 3x plus 1, so I'm just going to rewrite this expression. Absolute value, 3x plus 1. Then I subtract the limit. What's the limit? 7. That has to be less than 0.01. So I just plug in all the known information. So what will happen when you do that is this weird-looking red expression will turn into something much more concrete. Now we just have to evaluate that concrete thing and try and make it look like that. So a couple ways to do it. Let's put that on a new screen. We have much more room. Absolute value of 3x plus 1 minus 7 has to be less than 0.01. So first way is to just break down the absolute value to get rid of it, which means, and I guess we could clean that up right away. Is everyone okay with cleaning that up? What's that equal to? 3x minus 6. All right. So to get rid of the absolute value, I basically put less than on that side, greater than on that side. The greater than gets to keep whatever that number is. The less than on the other side gets the opposite of that. So the absolute value means just you have to be between the positive and negative versions of those numbers. And then solve this sucker for x. How do I solve this for x?
Add 6 to both.
And we would add 6 to both sides. So then we get 3x is less than 6.01 and greater than, add 6, sorry, 5.99 on that side. All right, so then we're going to get rid of the 3. So I divide blue, let's say, by 3 everywhere. And that's going to give us some unpleasant decimals. So I'm just going to leave it that way for now. So I get x is less than 6.01 over 3 and greater than 5.99 over 3. And I'm leaving it as a fraction because otherwise I have this decimal I have to think about rounding. I don't want to do right now. All right. I'm trying, again, to get something that looks more like that right there. So I need to get that minus a in there. Okay, what's a here? 2. All right, what do I do next to this? Minus 2 from everything. So minus 2, minus 2, minus 2. So, black. So now I have x minus 2, and then I get that, I guess I'll write it as negative 2 plus 6.01 over 3, and I get negative 2 plus 5.99 over 3. All right, so now whip out the calculator and calculate those two things and see what they are. So what is negative 2 plus 6.01 over 3? What is negative 2 plus 5.99 over 3? And in this case, I think they're going to look surprisingly similar. Feeling okay there? Sit up, take a deep breath. I know this is wicked exciting. Oh, I'm missing the last thing there, sorry. I had the same reaction first time I saw it.
The 5.99 side
Yep.
is negative 0.003 and then a bunch more threes.
Okay.
And the other side is the positive of that.
Ah, wicked cool. That's so basically the dare goes like this. You say, hey, I say I need to get within 100th of this, and you say fine, as long as you pick an x value that's within 1/3 of 100th, you got it, right? Because that's 1/3 of 100th right there, 0.003 repeating. So we found that we're close enough now. Cool. All right, so this is the like the Math 70 way, Algebra 1 way of doing this. So I'm going to do it with you a slightly different way just for fun. So I'm going to go back to my original interpretation of the inequality. That was 3x plus 1 minus 7. That absolute value has to be less than 0.01. Okay, so here's the other way to handle it. I'm going to do that little bit of algebra in there, so I have 3x minus 6. And I'm thinking about my goal. My goal was to get something that looks more like this thing right here, remember? Okay. So that means I want that 3 to go away, don't I? So I need to get rid of it. So I need to divide everything by 3. So let's do it. Divide by 3 here, divide by 3 there. Is the inequality okay if I divide by 3? Is it not going to flip on me, right? Yeah, if I divide by a negative, then I got to flip it, but I'm okay here. So what do I get? I get 3 goes into 3x x times. 3 goes into negative 6, negative 2 times. Holy crap, look at that. That was my goal. I'm there already, and that has to be less than 1/3 of 0.01, which is 0.003 repeating. Why did I do it the other way? Well, I did it the other way just to remind you of what the hell an absolute value inequality means. And it means you're looking on each side of some distance. And that exemplifies that. Okay. But here, if my goal is to just say how close do I need to be to A, I now have how close I need to be to A right there. I need to be within that distance of A. In this case, a is -2. So there's the result. Not too bad? All right.
So then the x value we would give you is.
You wouldn't give me an x value. So the way the question would work is the question would give you all of that stuff. And I would want to know how close should I be to x? Right? In other words, what is delta? And you would say be at least that close. The answer so that would be the answer in words. Okay, so I'm
Can
gonna
we just write that equation for the answer?
if this was on a physical test and I said, here's the function, here's a, here's the, I would ask you to find the limit.
Yeah.
And then I would give you epsilon and I would say, please find delta for me.
Okay.
Right? And if you wanted to get extra brownie points from me and look at your test and say, wow, they really thought about this, instead of just saying delta is 0.003 repeating, you would say that means be at least this close to x.
But why would anyone need to know how close we to x?
Because you're trying to justify me that you're right about the limit. So if I say I need to be within 100th of the limit for this to work out, you would say start this close. Okay. Suppose I'm building a bridge and I need things to line up and I have a whole bunch of pieces that fit together. This is like determining the margin of error for the people who are building stuff. So when you put it all together, you don't find that two ends of the bridge don't meet up. Right? So this is part of that process. If the beginning of the process says do all these steps to get to the end, and we know that the end of the process has to be this close, this tells us how precise we need to be when we start building things, when we start cutting the parts. Is a way to think about it in a production term point of view. So anybody here might be an engineer in the future? Yeah, so this is like engineering stuff. I need the end result of this process to be within 100th of the actual measurement we have, and you have all these other things to do to get there. So this would tell you how close you have to be when you start making each piece that's going to fit together. And when everything adds up, we should be close enough in the end. If you screw this up, then you're going to be too far off there, and things aren't going to fit. Right, that's another way to think about this process. All right, let's try a homework problem from this section. Let's see, that was from a different section. That's a different section. 2.5. All right, what are some exciting ones here? Number 5 was quite exciting. 6. Let's do 5. 6 is kind of cool. I'll actually show you that one first. 6 gives us a interactive program in Desmos to play with this stuff. So you enter your function, you tell it what a is. Here it wants delta, and then based on playing with delta, it will calculate epsilon for you. So this is an experimental approach. So for example, we just did what, 3x plus 1?
Yeah.
And we started with a was 2. And we just found if delta was 0.003333, then epsilon was going to be about 0.01. So this tool helps me experiment with that idea. Okay, so definitely check that out. I broke it. Okay. Number 5. So number 5 gives us this, that the limit as x approaches 6 of x squared minus 12x is equal to negative 36. We need to figure out delta as a function of epsilon. So here they're not saying epsilon is 0.01 or 0.001 or 0.05. They're just saying we're just going to call it epsilon, leave it variable. So that means delta will depend on it. So we're going to see what happens. So please write down this function. That's our starting point. So once we're given our function and we're trying to figure out what delta is, all right, so our goal here is to find delta. We just plug the given information into this inequality there. So f of x is x squared minus 12x. Then I'm subtracting a negative 36, so that's going to give me a plus 36. I'm going to simplify that part right away. So somehow I need to do some work and end up with, let's see, what's x is, a is 6. I need an x minus 6 is less than something. I need to make this look like that. That's the goal. So, multiple ways to attack this. Somebody suggest something.
We could factor it.
Ooh, it factors. Yes, that's a beautiful start. It factors as x minus 6 times x minus 6, doesn't it?
Sure.
Yeah, cool. Now I can write that with less ink, can't I? I could call it x minus 6 squared. Okay. I'm going to erase my goal for a minute. It's kind of in the way. Hey, if you square a number, is it ever going to be negative?
No.
So do I need the absolute value here?
No.
I don't even need it. That's kind of cool. This is working out pretty nice. Okay, how do we get rid of a square?
Square root.
Take the square root of each side. Man, we're rocking this. Okay, what happens when you take the square root of a square?
It drops.
No.
Turns into
Could be positive or negative.
no,
What other function do we know that could be, that deals with positives and negatives? What? The absolute value? Yeah, it turns out the square root of a square is actually the same thing as the absolute value. So it's back. But
Yes.
I'm done,
That's it.
right? Don't I have the absolute value of x minus 6? Isn't 6 my value for a? Yeah, so what must my delta be? The square root of epsilon, or smaller.
That's the answer.
That's the answer. Boom, done. Whoa. I know. This is weird. Takes some getting used to. Yeah, so if somebody says, I need you to be within a millionth of the limit, you would take the square root of a million and say, okay, be at least this close to 6. That'll get you there. Is what that tells us. So we've got what? Oh, we got no time left. I'm going to type in that, see if it works. So it says delta will be a function of epsilon. Did we find a function of epsilon?
Yeah.
Yeah, square root of epsilon. How do you type epsilon? You just type epsilon, the word. So SQRT, epsilon. And if you type it right, it'll say, oh, you want that little squiggly E guy. And I'd say, yep, I do. Notice before the parentheses, it gave me, you have a syntax error on matching parentheses. Right, so it's giving me tips. If you're not sure, hit the arrow, zoom out a little. And then I want the square root symbol. And do you have any epsilons hiding up there?
No.
No. Damn, it's not in there. I still got to type epsilon. I was hoping it was in there. Okay. So I'm going to save that and just type epsilon. Epsilon. William, you have an idea?
You could probably find the epsilon character.
Yeah, it's in the character map. Will that work if you plug in the, I think it would probably work.
I don't know.
I'll have to try that
math
later.
is kind of finicky.
Yeah, sometimes it can be. Like if you type the character code for a square instead of doing #2, I think my open math doesn't like that, but I'm not positive. Sometimes it doesn't like stuff. And so if you have any doubts about it, if you think you did it right and it marked you wrong, message your instructor. Okay. Question number 6, remember, has that nifty tool for doing it experimentally, and most of the answers are experimental. Like, give me a number that works. Okay. So good luck with those. They're a little tricky. We'll do some more of these tomorrow, and then we're going to start chapter 3.